Hello everyone. In this video, we're going to look at what we mean when we talk about the derivative of a function. So let's talk first off about how we would find the slope of a tangent line to a function at a particular point. So that's generally what we mean when we say, so let's say x equals 2, this goes through the point 2, 4. The slope of this function, well, if you have a linear function, the slope is constant, but this is a parabola and the slope is changing all the time. I can think of as x is getting bigger, this is getting steeper. But at a particular point, when we're talking of the slope, what we're talking about is if I were to draw a line tangent to the function at this point, what would its slope be? Now, the problem with finding this is in order to find slope, I need 2 points because slope is defined as the change in the y value over the change in the x value. But for a particular point, for one single point, my change is 0 for both vertical and horizontal. And as we've discussed with limits, we can't actually deal with that. That's an indeterminate form, 0 over 0. So we are going to use, like we did with limits, we're going to use the concept of a limit. So what I'm going to do is I'm going to say, okay, we have this point 2, 4. And on this tangent line, so I'm going to draw a line here. Let's say I have, oh, no, that is definitely not what I wanted to do. All right, I'll freehand it. All right, so we have a tangent line, let's say, and on that line, I'm going to take some other point. And this is going to be xy. But essentially, I want that x value to be getting closer and closer and closer to 2. So I'm going to find the limit of this slope as that x value approaches 2. So I'm going to actually use the function here. So the y value is x squared. So this point is x squared. This means that the slope between those 2 points, so the slope is the change in the y value, so x squared minus 4, over the change in the x value, x minus 2. I want the limit as x approaches 2 of this slope. Well, we've done this question before. This is factorable, so we can simplify by factoring. So x plus 2, x minus 2, which means that this limit, or this slope, the slope is equal to the limit of, as x approaches 2, of just x plus 2, which means that at this point, the slope is, the slope is equal to 4 at x equals 2. That's a pretty straightforward process for doing this. So the derivative is another word that we use here for the slope. So the derivative of this function when x equals 2 is 4, because the slope of this function when x equals 2 is 4. But more commonly when we're talking about the derivative, we're talking about the general formula. So find a formula for the slope of the tangent line to this same function for an unknown value of x. Now, that's not going to be a constant. That's going to be some new function because the slope is changing all the way along here. If x is bigger than 2, then my slope is actually going to be bigger than 4. If x is somewhere between 0 and 2, the slope is going to be less than 4. If x is less than 0, the slope has to be negative because the function is decreasing in that interval. So we actually want this second formula, this formula for the slope for an unknown value. And this is what we mean when we talk about the derivative. We're going to create a new function that allows us to calculate the slope at any point. So for this, I'm going to deal with the slope between some unknown value of x, which is x squared, and some other point that is going to be, and here's where this is a little weird. I'm going to take something that's a little ways away from x, and its y-coordinate therefore would be x plus h squared. So these are the 2 points I'm going to use. My unknown value of x and the y value, which I calculate using the formula, the function that's given, and then some value that's a little ways away from x. And then we are going to figure out the limit of this as h goes to 0. So as h gets closer and closer to 0, that means that this point will be closer and closer to my original point. So the derivative then the slope function, and I'll introduce some notation for that in a second, but for now I'll just use m because we know that for slope. So m is change in y over change in x, but I want the limit as h approaches 0 of x plus h all squared minus x squared, that's the change in the y values, over x plus h minus x. Or in other words, if I distribute and simplify this a little bit, the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared over the denominator where the x's cancel, so I just have h here. Which again, I can simplify a little bit further because the x squareds in the numerator are going to cancel, and I have 2xh plus h squared over h. I want to check this to see, well, can I just substitute in h equals 0? And I can't because the numerator would be 0 and the denominator would be 0. But I'm not done simplifying this expression because there is a common factor of h in the numerator. So I can divide both terms by h, and that gives me the limit as x approaches 0, or as h approaches 0, of 2x plus h. Now, as h approaches 0, if I just substitute this in, I get 2x. So the slope of this function at any given point is equal to 2x. Checking that against what I found before, I said when x was 2, the slope was 4. Well, that is 2 times 2. That also does kind of make sense if I think of symmetry, because if I were to go over to the other side of this when x equals 2, or when x equals negative 2, because of symmetry, I would expect this tangent line to be basically the same, but the opposite slope of the other side, and that makes sense. Also, sort of thinking through logically what's happening at the vertex. At the vertex, if I were to draw a tangent line, I would expect that to have a slope of 0. 2 times 0 is 0, so that works out here. So for ones where I can check, that does seem to make sense. And in fact, we've shown algebraically why it's true. The slope of the function at any point is equal to 2 times the x value of that function. Now, some notation here that we use. For the derivative, we have two different types of notation. One basically really does make clear that what we're dealing with is a slope, and it is dy dx. It makes a lot of sense if I think, well, slope is delta y over delta x, and when I'm talking derivative, my deltas are basically zeros. So the notation that got introduced was to use the letter d to indicate a change, a delta x or a delta y that was essentially 0. They're called infinitesimals. So dy dx is one notation for the derivative. So in this case, I can say dy dx equals 2x. The other notation, so that first one is what's called the Leibniz notation. It was the notation used by Leibniz, who was the German mathematician who developed a lot of these techniques. And then there's the Newton notation. Isaac Newton also developed many of these techniques concurrently in the UK. And so that notation is a prime notation, so f prime at x. The advantage of that one, if I'm dealing with functions, is that it makes very clear that I'm relating it back to the original function. It does obscure somewhat the fact that it is related to slope. We use both notations. They both have different contexts in which they might be better than the other, but both of them represent the derivative. So two different ways to express this. F prime of x equals 2x, or dy dx equals 2x. All right, let's follow this process with a different function, but essentially what we are finding, the derivative of f of x. So the derivative of f of x is f prime of x. It is equal to the limit, and I'm going to just write generically here as h approaches 0. So we're using h to represent our change. So the limit as h approaches 0 of f at x plus h minus f at x divided by h, because that's x plus h minus x. That's always going to happen in the denominator, so we can just always say, well, our denominator is going to be h. This is the definition of the derivative. So this is quite a critical formula here. But essentially, It is the slope formula. Definition. It's the slope formula where the points are getting closer and closer and closer together, hence the limit. So for this particular function, what that looks like, f prime of x equals the limit as h approaches 0. You need to keep that limit notation in there to indicate that it is a limit while we're still working with it, of 1 over x plus h minus 1 over x all over h. So that's what happens when I substitute in this specific function here. If I try and establish what that is, if I actually were to sub in h equals 0, my numerator would then become 1 over x minus 1 over x, which is 0. My denominator would be 0. This is an indeterminate form, so I have to do some manipulations. What I'm going to do in this case, so off to the side here, I'm just going to do some manipulations so I don't have to keep writing the limit definition. I'm going to change these so that they actually do have the same denominator. So I've got x minus h over x times x plus h, which is negative h over x times x plus h. So that is the numerator that I have in this, this limit. So what I have is the limit as h approaches 0 of negative h over x times x plus h all over h, in which case the h is going to cancel. So I end up with the limit as h approaches 0 of just negative 1 over x times x plus h. At this step, because I now have a negative 1 in my numerator, even if I still ended up with a 0 in the denominator, which we're not going to, we could at least reason our way through. So f prime of x is equal to, now I can drop the limit because I'm just substituting in at this point, negative 1 over x times x, because if h is 0, x plus h is just x, so x squared. So this is the function for the derivative. If I now wanted to know, well, what's the slope when x equals 7, I could simply plug 7 into this derivative. So something like this notation. So if I see f prime at 7, this means the slope when x equals 7. And I can simply just substitute it in here and say, well, when x equals 7, the slope would be negative 1 over 49. So that's the nice thing about getting a new function, is I don't have to redo my limit stuff every single time. Yeah, so a comment about this, if the limit doesn't exist, it's because the derivative doesn't exist. And this can happen for a few reasons. If the function is discontinuous at that point, then it doesn't have a derivative at that point. The function has to actually exist and be continuous. But also there are times where a function does exist and is continuous, but maybe it has an infinite slope. Maybe it has a vertical tangent, in which case the derivative isn't going to exist because the tangent doesn't exist. Maybe it has, so for example, in this case, if x equals 0, we don't have a derivative, and that's because the function actually doesn't exist at that point. But it could be because you have a vertical tangent. It could be because it's possible to draw more than one tangent. We'll explore that in a little more detail in class.